Engineers have had to develop very clever algorithms and ways of trying to store information in quantum computer memory and build the memory such that it's resilient to errors. Quantum mechanics has always been the domain of the bizarre and counterintuitive, but recent discoveries are pushing the boundaries of what we thought possible. Imagine a world where atoms, the building blocks of all matter, can communicate and synchronize with one another in free space without physical contact. It sounds like science fiction, but this is the new reality unfolding before our very eyes. In today's video, we'll dive into the groundbreaking discovery of atoms synchronizing in free space, explore how it works, and uncover the implications this could have for the future of science, technology, and our understanding of the universe. The discovery starts with the concept of synchronization, a phenomenon we see in nature all the time. Think of a flock of birds moving in perfect unison, or a group of fireflies lighting up simultaneously. This kind of collective behavior has fascinated scientists for centuries. However, observing such synchronization at the quantum level between individual atoms was something researchers could only theorize about until now. For years, quantum physicists have grappled with understanding how particles behave under certain conditions. Quantum entanglement, quantum superposition, and quantum coherence are terms we've heard before. They describe how particles can exhibit interconnected behaviors in ways that defy classical logic, but synchronization adds a new layer to this puzzle. It's not just about particles being connected through entanglement, it's about them harmonizing their actions as if they're part of a grand orchestra, even when separated by empty space. To understand how scientists achieve this feat, we need to look at the technology behind the experiment. At its core, the discovery was made possible through the use of ultra-cold atoms and highly specialized lasers. When atoms are cooled to temperatures close to absolute zero, their quantum properties become more pronounced. At these temperatures, atoms slow down significantly, making their behavior easier to observe and control. This is where the magic begins. The researchers used optical tweezers, which are highly focused beams of laser light, to trap and manipulate atoms. Individual atoms. By placing these atoms in free space, completely isolated from external influences, they created the ideal conditions for studying quantum interactions. Then they introduced carefully calibrated light pulses to influence the atom's internal states. What they observed next stunned the scientific community. The atoms began to synchronize their quantum states, aligning their energy levels and oscillating in perfect harmony. It was as if these atoms, separated by small distances in free space, were talking to each other and agreeing to act as one. This synchronization occurred without any physical connection or external mediator, a phenomenon that challenges our current understanding of quantum mechanics. So how is this possible? To answer that, we need to delve deeper into the quantum world. Atoms have internal states that are governed by quantum mechanical rules. When these states are manipulated using external forces like light, they can influence one another through a process known as quantum coherence. Coherence is the property that allows quantum systems to maintain a consistent relationship between their states over time. In this case, the atoms were able to achieve coherence, leading to synchronization. But there's another layer to this story. The key to the synchronization lies in the interaction between the atoms and the photons in the laser light. Photons, the fundamental particles of light, act as messengers, carrying information between the atoms. Even though the atoms are not physically touching, they can exchange energy and information through the photons, creating a feedback loop that drives synchronization. This is an entirely new way of thinking about quantum systems. The implications of this discovery are profound. First and foremost, it provides new insights into the nature of quantum mechanics. For decades, physicists have debated whether quantum behavior is inherently random or if there are hidden patterns waiting to be uncovered. The observation of synchronization suggests that quantum systems may have an underlying order that we're only beginning to understand. This breakthrough also opens up exciting possibilities for quantum technology. Quantum computers, which rely on the principles of quantum mechanics, could benefit significantly from these findings. One of the biggest challenges in building quantum computers is maintaining coherence between qubits, the quantum equivalent of classical bits. Synchronizing atoms in free space could provide a new method for creating highly stable and interconnected qubits, paving the way for more powerful and efficient quantum computers. Beyond computing, this discovery could revolutionize quantum communication. Imagine a network of synchronized atoms transmitting information across vast distances without the need for physical connections. This could lead to the development of ultra-secure communication systems based on the principles of quantum cryptography. Synchronization could also play a role in quantum sensing, allowing us to build more precise instruments for measuring time, gravity, and other fundamental properties of the universe. But perhaps the most intriguing aspect of this discovery is its potential to unlock new mysteries about the universe itself. If atoms can synchronize in free space, what does this say about the nature of reality? Does it imply that the universe is fundamentally interconnected, with particles influencing one another in ways we can't yet comprehend? Mokaku, a renowned physicist, has suggested that this discovery could point to deeper layers of reality, possibly even supporting theories about the multiverse or hidden dimensions. The idea of synchronization also resonates with philosophical and metaphysical questions. For centuries, thinkers have pondered whether the universe operates like a grand symphony, with all its parts harmonizing to create a coherent whole. The observation of atoms synchronizing in free space lends credence to this notion, suggesting that there may be a universal principle of order underlying the apparent chaos of quantum mechanics. As with any groundbreaking discovery, there are still many unanswered questions. For instance, what are the limits of synchronization? How far apart can atoms be and still synchronize their states? Can this phenomenon be extended to more complex systems, such as molecules or even biological structures? Scientists are eager to explore these questions, and the answers could lead to even more astonishing revelations. The road ahead is both promising and uncertain, challenging and exciting. Developing the technology to harness atomic synchronization on a practical scale will require years of research and innovation, but the potential rewards are enormous. Imagine a future where quantum synchronization enables us to build computers that are millions of times more powerful than today's supercomputers. Imagine communication systems that are completely secure and instantaneous, connecting people across the globe in real time. Imagine using synchronized atoms to probe the mysteries of black holes, dark matter, and the origins of the universe. This discovery also highlights the importance of international collaboration in science. The experiment was made possible by a team of researchers from around the world, each bringing their unique expertise to the table. It serves as a reminder that the pursuit of knowledge knows no boundaries, and that the greatest breakthroughs often come from working together. As we reflect on this quantum discovery, it's clear that we are entering a new era of scientific exploration. The synchronization of atoms in free space is not just a technical achievement, it's a glimpse into the future of quantum mechanics and a testament to the power of human curiosity. It challenges us to think bigger, to ask deeper questions, and to embrace the unknown. In conclusion, the discovery of atoms synchronizing in free space is a landmark achievement that will reshape our understanding of the quantum world. It opens up new possibilities for technology, challenges our assumptions about reality, and inspires us to keep exploring the mysteries of the universe. As scientists continue to push the boundaries of what's possible, one thing is certain: the quantum revolution has only just begun. The concept of quantum synchronization is not just a breakthrough in physics, it's a phenomenon that invites us to rethink how the universe operates on its most fundamental level. To truly grasp the magnitude of this discovery, let's dig deeper into its potential applications, the challenges it presents, and the profound questions it raises about the nature of reality. Let's start by looking at how quantum synchronization connects to a broader understanding of quantum coherence. At its core, coherence is what allows quantum systems to maintain the predictable relationship between their states over time is crucial. Without coherence, the delicate balance that defines quantum systems collapses into chaos, rendering them ineffective for practical applications like quantum computing or communication. Synchronization builds on this concept, offering a mechanism by which coherence can not only be maintained but actively amplified. By observing atoms aligning their internal quantum states in free space, scientists have stumbled upon a new method for preserving coherence over longer distances and timeframes. This discovery has far-reaching consequences for quantum computing, where qubit stability has always been a critical limitation. Take quantum computers, for example. Unlike classical computers, which rely on binary bits of information ones and zeros, quantum computers use qubits, which can exist in a superposition of states. This allows quantum computers to process vast amounts of information simultaneously, making them exponentially faster and more powerful for specific tasks. However, qubits are notoriously fragile. Any interaction with their environment can disrupt their quantum state, a phenomenon known as decoherence. Now imagine using quantum synchronization to combat decoherence. If qubits can be synchronized in free space, maintaining coherence even in the face of environmental disturbances, it would revolutionize the field of quantum computing. This would lead to machines capable of solving problems that are currently impossible, such as simulating complex chemical reactions, optimizing global supply chains, or even deciphering the mysteries of protein folding to unlock cures for diseases. But synchronization's potential doesn't stop at computing. One of the most exciting applications lies in the realm of quantum communication. Today's internet relies on classical methods of transmitting data, which are inherently vulnerable to interception and hacking. Quantum communication, on the other hand, offers unparalleled security. By encoding information in the quantum state of particles, scientists can create communication channels that are fundamentally unhackable. Any attempt to intercept the data would immediately disrupt the quantum state, alerting the sender and receiver to the intrusion. The discovery of quantum synchronization could take this a step further. Instead of relying on physical connections like fiber optic cables, synchronized atoms in free space could act as the nodes of a quantum network, transmitting information instantaneously across vast distances. This concept, often referred to as a quantum internet, could revolutionize how we share information, making global communication faster, more secure, and more efficient than ever before. And it's not just communication that stands to benefit. Synchronization could also enhance quantum sensing, a field that involves using quantum phenomena to measure physical quantities with unprecedented precision. For instance, synchronized atoms could be used to build highly accurate atomic clocks, which are essential for applications like GPS navigation, telecommunications, and scientific research. These clocks could be so precise that they lose only 1 second every billion years, enabling us to measure time and space with unparalleled accuracy. Another intriguing application lies in the study of fundamental physics. By using synchronized atoms as ultra-sensitive detectors, scientists could probe the mysteries of dark matter, gravitational waves, and other phenomena that lie at the edges of our understanding. This could help answer some of the most profound questions in science. What is the true nature of dark matter? Are there hidden dimensions in the universe? And what lies beyond the observable cosmos? But as exciting as these possibilities are, they also come with significant challenges. For one, achieving synchronization at larger scales will require advances in both theory and technology. While current experiments have demonstrated synchronization between a small number of atoms, scaling this up to more complex systems will be a daunting task. Scientists will need to develop new methods for controlling and manipulating quantum systems, as well as address the practical limitations of current technologies. Another challenge lies in understanding the fundamental principles behind synchronization. While we know that coherence and photon-mediated interactions play a role, the exact mechanisms are still not fully understood. This opens up a fascinating avenue for further research. As scientists work to unravel the deeper laws governing quantum synchronization, these insights could lead to new discoveries that reshape our understanding of the quantum world and its connection to the macroscopic universe. And then there are the philosophical implications. The synchronization of atoms in free space raises profound questions about the nature of reality. At the quantum level, particles behave in ways that defy our classical intuitions, exhibiting properties like superposition, entanglement, and wave-particle duality. Synchronization adds a new dimension to this mystery, suggesting that even isolated particles can exhibit collective behavior as if governed by a hidden order. This has led some scientists and philosophers to speculate about the existence of a deeper layer of reality. Could synchronization be evidence of a universal principle that connects all matter and energy? Is it possible that the universe itself operates as a kind of quantum symphony, with every particle playing its part in a grand cosmic harmony? These are questions that challenge not only our scientific understanding, but also our philosophical and spiritual beliefs. The discovery also invites us to rethink the concept of individuality at the quantum level. If particles can synchronize their states and act as a unified whole, what does this say about the nature of identity and separateness? Are particles truly distinct entities, or are they part of a larger interconnected system? These questions have implications that extend beyond physics, touching on fields like biology, neuroscience, and even sociology. For example, consider the parallels between quantum synchronization and phenomena observed in living systems. From the synchronized firing of neurons in the brain to the collective behavior of cells in a developing embryo, nature is full of examples of individual components working together as a cohesive unit. Could the principles of quantum synchronization help us understand these biological processes? And if so, could this lead to new breakthroughs in medicine, neuroscience, and biotechnology? One particularly intriguing possibility is the idea of using synchronized atoms to create new forms of artificial intelligence. Today's AI systems are based on classical computing, which has its limitations. By harnessing the power of quantum synchronization, we could develop AI systems that are not only more powerful, but also more intuitive and adaptive. These systems could process information in ways that mimic the human brain, leading to advances in areas like robotics, natural language processing, and decision-making. As we consider these possibilities, it's clear that quantum synchronization is more than just a scientific breakthrough. It's a window into a new era of exploration and innovation. It challenges us to think beyond the limits of our current understanding and to embrace the unknown. It reminds us that the universe is far more complex and mysterious than we can imagine, and that the quest for knowledge is an ongoing journey. In the coming years, we can expect to see rapid advances in this field as researchers build on the foundation laid by this discovery. New experiments will push the boundaries of what's possible, exploring synchronization at larger scales, in more complex systems, and under different conditions. These efforts will not only deepen our understanding of quantum mechanics, but also pave the way for practical applications that could transform our world. At the same time, this discovery serves as a powerful reminder of the importance of basic research. The study of quantum synchronization may have practical benefits, but its true value lies in its ability to expand our understanding of the universe. It's a testament to the power of curiosity in the human spirit, showing us that even the smallest particles can hold the keys to the biggest questions. As we look to the future, one thing is certain: the discovery of quantum synchronization is just the beginning. It's a stepping stone to new realms of knowledge, a glimpse into the infinite possibilities of the quantum world. As we continue to explore this frontier, we can only imagine what other wonders await us. Quantum synchronization is not merely an isolated discovery, it's a transformative lens through which we can reconsider our understanding of the cosmos and its inherent mechanisms. Let's delve even further into the philosophical, scientific, and technological revolutions that this represents. Breakthrough heralds a new paradigm for understanding the quantum world. When we think about quantum mechanics, we are often reminded of its enigmatic principles, such as superposition, entanglement, and wave-particle duality. Quantum synchronization, however, builds a bridge between these principles, demonstrating how isolated quantum systems can self-organize into coherent patterns. In many ways, it's like finding order in chaos. Consider this: the classical world we interact with every day is governed by predictable laws, such as Newtonian mechanics. Yet, the quantum world operates on principles that, at first glance, seem entirely counterintuitive. Synchronization challenges this apparent dichotomy by revealing a hidden harmony underlying the unpredictable behaviors of quantum particles. For decades, physicists have worked to reconcile quantum mechanics with classical physics through theories like quantum field theory and attempts at quantum gravity. Synchronization now suggests that the gap between these realms may not be as vast as once thought. If atoms can synchronize across free space without direct interaction, it hints at an unseen universal mechanism that fosters coherence across all scales of existence. This revelation could pave the way for a unifying theory that not only connects quantum mechanics to general relativity, but also reveals entirely new aspects of reality. Could quantum synchronization be the missing link in our quest for a theory of everything? It's a question that will undoubtedly drive scientific inquiry for decades to come. The universal symphony, synchronization beyond atoms. The concept of synchronization extends far beyond the atomic scale. Throughout nature, we see countless examples of systems that exhibit synchronized behavior. From the beating of human hearts to the flashing of fireflies and the movement of celestial bodies. This raises an intriguing possibility. Could the principles of quantum synchronization underpin all these phenomena? For instance, think about the human brain. Neurons fire in intricate patterns, creating waves of electrical activity that govern thought, emotion, and consciousness. While this activity is typically explained through classical biological processes, synchronization at the quantum level could offer a deeper explanation. What if the brain's coherence arises not just from biochemical interactions, but also from quantum phenomena? If this hypothesis proves true, it could revolutionize neuroscience and artificial intelligence. By harnessing the principles of quantum synchronization, we could design neural networks and AI systems that mimic the brain's quantum coherence. These systems would not only be faster and more efficient, but also capable of creative and adaptive thinking far beyond the capabilities of current AI. Furthermore, synchronization may shed light on one of the greatest mysteries of all: consciousness itself. Some physicists and philosophers have long speculated that quantum mechanics plays a role in the emergence of consciousness. Synchronization provides a tangible mechanism by which this might occur, suggesting that our awareness arises from the collective behavior of quantum particles within the brain. Synchronization in cosmology, the building blocks of the universe. On a cosmic scale, synchronization could hold the key to understanding the origins and structure of the universe. When we look at the night sky, we see stars, galaxies, and nebulae arranged in intricate patterns. These structures didn't emerge randomly. They formed through processes governed by the laws of physics, including gravity, electromagnetism, and quantum mechanics. Quantum synchronization offers a new perspective on these processes. Just as atoms can synchronize their states in free space, it's possible that particles in the early universe exhibited similar behavior. This could help explain phenomena like cosmic inflation, the rapid expansion of the universe that occurred just moments after the Big Bang. Synchronization might have played a role in shaping the distribution of matter and energy, leading to the formation of galaxies and other large-scale structures. Moreover, synchronization could help us understand the mysterious dark matter and dark energy that make up most of the universe. While these phenomena are currently explained through classical physics, it is possible that their true nature lies in the quantum realm. By studying synchronized systems, we might uncover new clues about the fundamental forces that govern the cosmos. As we push the boundaries of quantum research, we must also consider the ethical and philosophical implications of our discoveries. Quantum synchronization raises profound questions about the nature of reality, individuality, and free will. For example, if particles can synchronize their states and act as a unified whole, what does this mean for our understanding of identity? Are individual particles truly separate entities, or are they part of a larger interconnected system? This question has implications that extend far beyond physics, touching on fields like philosophy, sociology, and even theology. Some philosophers have drawn parallels between quantum synchronization and ancient spiritual concepts, such as the idea of oneness or the interconnectedness of all things. While these ideas have traditionally been dismissed as metaphysical or unscientific, synchronization provides a tangible scientific basis for them. This has led to a renewed interest in the relationship between science and spirituality, as researchers explore the ways in which quantum mechanics aligns with philosophical and religious traditions. From a practical perspective, the discovery of quantum synchronization opens up a wealth of technological possibilities. As mentioned earlier, synchronized atoms could revolutionize quantum computing, communication, and sensing, but these are just the beginning. One promising application lies in the field of energy. By leveraging synchronization, scientists could develop new methods for harvesting and storing energy with unprecedented efficiency. For instance, synchronized systems could be used to create highly efficient solar panels, batteries, and other devices. These technologies would not only reduce our reliance on fossil fuels, but also enable the development of sustainable energy solutions for the future. In medicine, synchronization could lead to breakthroughs in imaging, diagnostics, and treatment. For example, synchronized quantum sensors could be used to create highly advanced tools for medical applications. Ultra-sensitive imaging devices capable of detecting diseases at their earliest stages could also be used to study biological processes at the quantum level, leading to a deeper understanding of how the human body functions. Synchronization could even play a role in space exploration by creating synchronized systems capable of operating in extreme environments. Scientists could design spacecraft and instruments that are more resilient and efficient, enabling us to explore new frontiers. From the icy moons of the outer solar system to distant exoplanets in other star systems. Challenges and the road ahead. Of course, realizing these possibilities won't be easy. Quantum synchronization is a complex and delicate phenomenon, and scaling it up for practical applications will require significant advances in technology and theory. Scientists will need to develop new methods for controlling and manipulating quantum systems, as well as address the practical limitations of current technology. One major challenge lies in maintaining synchronization over long distances and timeframes. While recent experiments have demonstrated synchronization between a small number of atoms in free space, extending this to larger systems will require precise control and stability. This will likely involve the development of new materials, technologies, and techniques. Another challenge is understanding the fundamental principles behind synchronization. While we know that coherence and photon-mediated interactions play a role, the exact mechanisms are still not fully understood. This opens up a fascinating avenue for further research as scientists work to unravel the deeper laws governing quantum synchronization. Finally, there are the ethical and societal challenges associated with this discovery. As with any technological breakthrough, we must consider the potential risks and unintended consequences of quantum synchronization. For instance, how do we ensure that these technologies are used responsibly and ethically? How do we address issues of security, privacy, and inequality in a world shaped by quantum technologies? The dawn of a quantum era brings both incredible promise and profound responsibility. Despite these challenges, the discovery of quantum synchronization marks the beginning of an exciting new era. It's a reminder of the boundless potential of human curiosity and ingenuity, and a testament to the power of science to unlock the mysteries of the universe. As we continue to explore this frontier, we can only imagine what other wonders await us. From the smallest particles to the largest structures in the cosmos, synchronization reveals a hidden order that connects us all. It's a glimpse into the infinite possibilities of the quantum world and a call to embrace the unknown. For